Good morning, it's Mrs. Dr. B. We are going to talk today about ideal gases and the ideal gas law and the combined gas law. We have other videos that we are watching on all the individual gas laws, Avogadro's, Boyle's, Charles, and Gay-Lussac. They all operate off of this thing right up here called the ideal gas law, and you can find each one of the laws within this law, or you can find each one of the relationships within the law. So let's first of all just kind of talk about what ideal gases are. They're also known as perfect gases, and we know that perfect doesn't exist very often in nature. But we talk about gases being ideal when they do not have any attraction. The molecules within them or the particles within them do not have any attraction to each other, which means there's no intermolecular forces, and that every collision that they make, whether it's with another gas molecule or with the container, is perfectly elastic, which means a gas molecule doesn't lose energy when it hits something else. So again, there's some very specific conditions. When we talk about ideal gas laws, we talk about how gases deviate from this, but really and truly what we really want to use is this idea that this ideal gas law, PV equals nRT, shows us the relationship between the conditions of the gases as we talk about them. All right? So again, most studies use this as the foundation, and the reason is because they can be every relationship can be described within the law, written as it is written right here. Pressure and volume are indirectly proportional. When one goes up, the other one goes down. Pressure and temperature, when one goes up, the other one goes up. Volume, when volume goes up, temperature goes up, or vice versa. When moles go up, volume goes up. So all of the laws are found within this ideal gas law, which makes it so wonderful to use as a foundation for every gas law problem you ever work. All right, so again, pressure exerted by the gas. We know that gases produce pressures because they collide with the walls of their container, because they fill the container. We need to talk about the volume of the container. This is done in liters in the ideal gas law. The amount of gas, which is in moles, which is N. The temperature of gas has to be in Kelvin. And then we have that thing called R. We'll talk about that in a moment. All right, P, V, N, R, T. Most everybody doesn't look at that equation and just say, oh, that's PV equals nRT. No, most people say that's PIV-NERT. And so whenever you hear somebody talk about PIV-NERT, you know they're talking about the ideal gas law. All right, so let's talk about this ideal gas constant. It's constant. It is a number that is set based on 1 mole of gas at standard temperature pressure. So if you remember what standard temperature and pressure are, then you're going to be able to kind of fill this out. It's something you actually have to try to work at. You can't just simply know this. So let's rearrange the equation PIV-NERT to show you what the units are. All right, so let's just take it and isolate R by dividing both sides by N and T. We can see that the N and the T cancel, and you end up with PV over NT equals R. So let me do this over here. PV over NT is equal to R. V is always in liters. N is always in moles. T is always in Kelvin. But pressure has lots of different, we'll call them units of measurement. So it is this one right here, pressure, that determines the value of the ideal gas constant. All right, so there's 2 of them we're going to use. And so what we have to do is we're going to just fill in the numbers. Please understand these numbers never change. That's why it's called a constant, right? So the first number we're going to fill in is 1 mole because it is based on 1 mole of material at standard temperature pressure. All right, well, we know that 1 mole from Avogadro of anything at standard temperature pressure has a volume of 22.4 liters. That number never changes. We understand that at standard temperature is 273 Kelvin. That number never changes. So 3 of the 4 numbers here never change. However, if atmosphere or pressure is done in kilopascals, then what we know is it becomes 101.325. You calculate this number, and what you're going to get is this value right there. You're going to get that value. If you decide to do this with atmosphere, you'll find that moles stays the same, liters stays the same, Kelvin stays the same, but the only difference is now you're dealing with 1 atmosphere. And so when you calculate this R, we're going to get this other number up here at the top. So you have to really kind of sort of know these, and you honestly should just take the time to learn this. It just helps. All right, so let's think about some ideal gas law problems. How they work. I'm going to work a couple of these. They're in here. I'm not going to take a lot of time because I do not want this to be a really long video for you. With ideal gas laws, we're not asking to consider how pressure, volume, temperature, any moles changes from a before and an after. What we are always doing is comparing pressure, volume to the standard conditions. That's why R is in there. You're going to have one factor that's missing. All the other factors will be given. Again, remember the value of R depends on the units of pressure. Volume has to be in liters. Temperature has to be in Kelvin. All right, so let's look at practice problem number 1. It reads, I have 7.8 volumes of moles of gas. All right, that's N. And you'll see that I've listed it right down here in the page, N equals 7.8 moles. We know that it is at 130.872 kilopascals. So let me just go ahead and write those up there anyway. 7.8 moles. We have pressure, which is 130.872. This is in kilopascals. This already tells you that we will be using the bottom R. We see that it takes up volume 13.77 liters of space. What are we looking for? We're looking for temperature. So we have R, which is 8.314 kilopascal liters per mole Kelvin. We have P, we have V, we have N, we don't have T. Now I don't have to have it set up for R. I can use the equation right here and just put my numbers inside the equation and then solve for the one that's missing. It's the easiest way to work these problems. Don't rearrange anything. Put the numbers straight in. Then you can simplify. Now, I'm putting in these units every single time because I want to cancel them. Alright, so watch me cancel these units. I've got kilopascals on the left. Right, I've got kilopascals that when I actually do the math on the right are going to cancel. Liters are on the left. Liters are on the right. We see right here moles on the right and moles on the bottom of the right. So the only units that's left is temperature. That's what we're looking for. So the units really, really do make a difference. If you look at this is going to be the math setup. What you're going to do is you're going to multiply those, simplify that's the left, then divide by the 7.8 and 8.314 from the right, and what you're going to end up with as a value is T is equal to 27.79 Kelvin. So all we've done is we have simply just substituted everything in. Alright, let's go to problem number 2. We're asking for what volume container. We are looking for volume here. Alright, so let's take this all off. We know we have 4.4 moles of N. We know that we are at 0.87 atmospheres. That tells me I'm going to be using the top version for this problem. Alright, what else do we have? We have 213 Kelvin. Alright, what don't I have? I don't have volume, and look, that's what I marked already. We know what we have. So let's just put everything in. P, 0.87 atmospheres times volume, which we don't know. N is 4.4 moles times R, 0.0821 atmosphere liters per mole Kelvin, and we know we have 213 Kelvin. Let's see if our units give us volume, atmospheres, or excuse me, let's go with Kelvin first, both sides on here. Let's look at moles. Moles is on the top and on the bottom. It cancels. I have atmospheres on the left and I have it on the right. They will cancel. And look, the only units that are left are liters, which is volume. Alright, so we will multiply everything together here on the right, and we will divide by 0.87, and we will get a volume that is equal to 88.44 liters. These are very simple problems. The biggest thing you need to do is you need to be able to assess what your units of pressure are, and based on that you need to decide which R value you're going to use, and otherwise it's a matter of substituting in. Alright, let's move on. Practice problem number 3. Alright, practice problem number 3 says, how many moles of gas? We know we are looking for N. We are looking at volume. I'm not going to do this, I'm just going to do this in order. 8.326 milliliters. Alright, when a gas is at pressure is 5643 kilopascals, and the temperature is 45 degrees Celsius. What don't we have here, guys? We don't have moles. We already knew that from the beginning. We know what R is going to be. It's going to be the bottom R because we're talking about kilopascals. So the first thing we have to do, though, is we need to look at this. We've got to be in liters, right? So we're going to have to convert this. And we know that there's 1,000 milliliters in a liter, so there's your conversion for that one. And we know we're going to have to go from Celsius to Kelvin. So we're going to add 273. And then we're going to get our value there for Kelvin. So in our particular case, guys, Kelvin is going to be 318. And we can see that all we've done is divided this. We're going to have 83.226 liters. Alright, so all we have to do here is the exact same thing we've done before. Substitute all this information in to the formula. PV PV equals N we're looking for. We got R and we have T, and you can see that you're going to get an answer. N is equal to 1.78 liters. All right, so I'm going to stop this one right now, and I'm going to say we're going to come back and I'm going to do another quick video separated from this one, and it's going to be combined gas laws that shows you what happens when you are still looking at a before and an after, but you have more than two of the actual conditions. So it'll be the same PowerPoint, but I'm just going to break it into two different videos. All right, we'll see you in a few minutes. Bye.